All right, let's start with problem of the day 21. Problem of the day 21 was taking us back to first term. How many of you guys really remember acid-base chemistry? It's going to come back with a vengeance on the ACS exam, so we're going to try to throw in more problems that are review problems that are integrated with problems that are tied into more recent chemistry. If we compare compound A to compound B, the only difference is a couple of double bonds, right? Normally a nitrogen compound is going to be more basic than an oxygen compound, right? So if we look at something like ammonia, NH3, that's more basic than water. Why is that? Yeah, oxygen is more electronegative. There's two ways of thinking about this, right? If oxygen is forced to carry a positive charge and it's really electronegative, that makes it very unhappy. The other thing to think about is the lone pair on water is held very tightly by the oxygen because it is so electronegative. That means it's going to be less available to donate its electrons to a proton or a Lewis acid, right? So normally we would say nitrogen should be the more basic site. However, in this problem, it says that compound B, nitrogen is not the most basic site. Oxygen is. Why is that? Resonance could be a good answer. Let's take it one step further. What do we call superresonance? Yeah, aromaticity, right? So superresonance around a ring, we call it aromaticity. You get this extra stabilization when it's in a ring system. Perfect. So the big thing with compound B is, let's draw it a little bit on its side. We've got this p orbital here and here, and we're forming a pi bond. And we've got a p orbital right here and here, and we've got a pi bond. We also have this methyl group sticking over here, so I'll write CH3. Where's the lone pair on nitrogen? In a p orbital, right? Oftentimes people will look at the nitrogen on compound B and they'll say that lone pair should be in an sp3 orbital. However, if you remember back to first term, I said if you have a lone pair that can delocalize, that means it will occupy the p orbital and it will change the hybridization of that atom. So in this case, our lone pair is located right there. We've got two pi's and a p. How many total electrons do we have in our pi system? 6. That makes this aromatic. Another way you can look at this, I'm just going to erase this really quick, is using resonance. We could say, all right, if we dump this electron pair down, we can dump this electron pair over and over. And all of a sudden, we've got an aromatic structure where this oxygen now has a negative charge. Right? That makes this oxygen very basic. And we've got this aromatic ring, which is very, very stable. So if anything, the way I have compound B drawn above really isn't the major resonance contributor. In fact, the major resonance contributor will be the one shown on the right in the box. Even though there's charges there, that stabilization from aromaticity is what really drives that conformation. Does that make sense? A little bit tricky. Question 2 is looking at synthesis. We're trying to get our thinking brains back on with synthesis problems. There's a couple different routes. Does anybody have a recommendation for step 1? Radical bromination. All right. NBS, we can use UV or heat. Somebody said, does it matter? No, you just need to initiate it using some energy source. If we do that, we can install our bromine on our benzylic position. Now what? NaOH. Okay. What sort of reaction is this? SN2. Again, another first term reaction. And then, how can we go from, I'm just going to connect this with one big arrow, from our primary alcohol to our aldehyde? PCC, right? Why don't we use chromic acid? It'll over-oxidize it to benzoic acid, right? Did anybody have a different way that didn't use radical bromination? Chromic acid? Okay, that's another route. So let's say we use chromic acid, Na2Cr2O7, H2SO4, and water. What will that give us? Carboxylic acid, specifically benzoic acid. And then how can we get from benzoic acid to this alcohol? Yeah. Lithium aluminum hydride. We normally use excess, and then we follow this up with water, and that will get us to our primary alcohol that we can oxidize to benzaldehyde. One problematic thing is we can't oxidize the benzylic position directly to the aldehyde very easily, at least using the reactions that are presented in the Klein textbook. So oftentimes you have to do this procedure where you essentially take 2 steps forward, 1 step back, or 2 steps backwards, 1 step forward to get to the same product. There might not be a direct route. So tomorrow and later on today, I'll try to throw on some more synthesis problems that we can practice just to get thinking about that again. Make sense? All right. Let's go back to our chapter 18 notes. There was one correction I wanted to make to lecture from the other day. I forgot one of the parents. I did. There was one other parent system that I had slipped my mind. It looks pretty similar to a phenol, but it's got an NH2 group coming off. Does anybody know the name of this one? Aniline. So aniline, Aniline is another parent group that you will commonly see, and I believe it shows up in sapling. So I did want to put that up on our list of IUPAC accepted names. All right, let's go to reactions at the benzylic position. Yesterday we said we can oxidize the benzylic carbon to a carboxylic acid. We can do that 2 different ways, using chromic acid or potassium permanganate. But in order to do this, we have to have alpha protons. And we also said if you've got other alkyl spinach groups kind of hanging off, those get cleaved off during this oxidation reaction, and you trim it down to only 1 benzylic carbon. We ended talking about free radical bromination. Let's try to review the mechanism for this bromination really quick. What's the first step in free radical bromination? Initiation. Does anybody remember what MBS looks like? All right, it's a ring system. All right, we do a single-headed barb. We can't use a double-headed arrow in this example because we're not moving both electrons. That means we end up forming our bromine radical. And the reaction's initiated. Now that we have the bromine radical, we can take our compound from above, and we said that the most likely protons that will be abstracted will be one of these benzylic protons. And our bromine radical will abstract, whoops, that looks like a double-headed arrow, one of these protons, resulting in a benzylic radical that is stabilized by resonance. What's the next step? Not termination. We haven't installed our bromine yet. Close. Propagation, right? So in this NBS system, there's oftentimes trace bromine around. This radical will abstract a bromine atom from elemental bromine that's floating around in solution. All of a sudden, you've got your bromine installed. And you end up with a mixture of enantiomers because that radical electron is occupying a p orbital that is facing both in and out of the board, right? And during this reaction, we regenerate our bromine radical. What's the next step, Fiona? Termination. We can take our two bromine radicals, or any other radicals for that matter, and we can just have them coupled together, and we can form a covalent bromine-bromine bond. So I did want to review a little bit of radical chemistry because I know some people were rusty with it. All right. I'll slow down. I know I'm going kind of fast. You can drop your pen loudly when you're done. That way I know.
I just found my pod.
Okay. All right, let's continue on to some other reactions. One nice thing with benzylic positions is you can have some sort of halogen on here. I'll just use bromine as an example. And you can get to an alcohol two different ways. We saw one reaction where we used sodium hydroxide on our pod, right? And what sort of substitution was that? SN2, right? We've got a strong nucleophile. Why don't we do E2? You don't have any beta protons, right? That, and it's a primary carbon. Primary electrophiles prefer SN2 over E2, so we can get away with using sodium hydroxide. What about using something like water? Will this work? Well, let's think about this. What if the bromine fell off and we form a carbocation? It'd be a primary carbocation. Our gut instinct says, oh, that looks wrong. But it's on a benzylic carbon, right? Benzylic carbons are remarkably stable because they're right next to that big aromatic ring. That stabilizes the positive charge immensely. So with benzylic substitution, you can actually do SN1 or SN2 substitution. If you do SN1, you only need a weak nucleophile. If you do SN2, you have to use a strong nucleophile. We can also do basic elimination reactions. So I'm going to choose a new group. What would we name this benzene? Does anybody have an idea? Yeah, isopropyl benzene, right? It's got an isopropyl group coming off of it. Alternatively, we could call it 1-methyl-ethylbenzene if you want to get fancy with IUPAC. Either one works. And let's say I want to make this compound. Whoops, forgot my double bonds. Question is, how could we do this?
NBS.
Okay, so let's say we do NBS and we do UV light. That will install a bromine onto our benzylic position, which is right here. And then what?
An H.
Yeah, some sort of strong base, right? So let's say we use a strong base. We can actually use any strong base we want because we're not worried about Hofmann versus Zaitsev in this case. There's no beta protons on that aromatic ring. So I'm just going to arbitrarily use sodium methoxide. And this would be our E2 elimination because we're using a strong base. All right. Alternatively, what if we want to do this with an E1 reaction? What could we do to form or do this reaction using an E1 mechanism?
Do we have to?
Yeah, just for the sake of argument.
Oh, so just for one?
Yeah, just for fun. You guys don't do this for fun at home? Let's do the same thing. NBS, UV light, but we want to do E1. Does anybody have an idea? With E1, do we want to use a strong base? No. What do we want to use? Water. So we could use water, and water might do substitution, so we might observe some SN1 products. How can we get this to favor E1 products? Heat. So we can do E1 or E2 reactions. We also have one other one. Let's say I've got a benzylic alcohol and I want to still form the same product. What could I do?
Oxidize it.
Not oxidize it. We don't have alpha protons. We can't oxidize it. Does anybody else have an idea? So you could tosylate it. However, we'd still be doing an E2 route. We can get there one step. If we're trying to be green chemists here, we want to try to limit the number of steps, avoid nasty bromine reagents.
H3O.
Yeah, strong acid and what else? And heat, right? So elimination, right? So we could also do something like catalytic acid. So we could put in a drop of sulfuric acid or phosphoric acid, for example, and we can heat this. And this is also similar to an E1 mechanism. So we can do E1 with benzylic alcohols very, very easily, one-step reaction, and form this styrene derivative. Does that make sense? A lot of review. The cool thing with these reactions is they kind of intercept the reactions that we've covered in the rest of the chapter, or the rest of the book for that matter. And I pulled this chart from, I think it was the back of chapter 18 in the Klein textbook, but it shows how this gets linked into other chemistry. So if you look in this corner, we've got radical bromination or oxidation. If we put in a bromine, we can do SN1 or SN2, we can get to an alcohol, and then we can do all of the alcohol chemistry that we covered in a previous chapter. If we go to benzylic acid, or benzoic acid, we can also get to an alcohol like we saw in our POD by doing reduction. Alternatively, we could do radical bromination, do SN1, get an alcohol, do reaction of that tertiary alcohol. We could do E1 or E2 elimination, get an alkene, and do any of the reactions from chapter 9. And we can even turn alkenes into alkynes and do all sorts of crazy stuff. So this is another tool to add into our toolbox, but we're going to start using these in synthesis problems now. Does that make sense? So you guys have more to add into your reaction maps. It's going to get bigger and bigger. All right, last reaction of Chem 262. I promise. Let's recall one reaction, and we're going to do a similar one to this. Let's say we have styrene, and I want to convert styrene to ethylbenzene. What reagent do I need? H2 and palladium, nickel, platinum, one of those catalysts. And typically we run this under relatively low pressure. And what I mean by low pressure is it's about the same pressure as if you opened up a can of soda, right? You don't need to crank the pressure up too high to get this reduction to work. What if we want to reduce the aromatic ring? Yeah, super high pressure. And you can do this, but you have to use typically a different catalyst, and you have to use 3 equivalents of hydrogen gas. And typically this requires about 100 ATM, which is a huge amount of pressure. Most labs are not equipped to handle that sort of high pressure chemistry. So you very rarely see this done. I think the only place in the state of Washington that will do this is a handful of labs at UW and Hanford. Your average organic chemistry lab will not do this reaction. There's also another type of reaction that's similar to these called the Birch reduction. All of the above reactions were reductions, but the Birch reduction will actually reduce a benzene ring under relatively mild conditions. However, it won't reduce it all the way to the cycloalkane derivative. With the Birch reduction, instead of reducing all of the pi bonds, it will just do a 2-electron reduction. And in order to do this, we have sodium. And what does that little circle mean in the top? Elemental, right? So it's not a sodium ion, it's elemental sodium. It's the metal. We have methanol. And we have ammonia. So let's take a look at this. Does this look familiar to any other reaction that we've seen? What was the other reaction where we used sodium and ammonia? Yeah, if we want to get a trans alkene, we can take an alkyne and do dissolving metal reduction. So this is really similar to that, but it's with benzene rings. And so let's take a look at the mechanism. I'm going to draw in all of our hydrogens at first. They're clapping for me. We've got sodium. How many electrons does sodium have? 1 valence electron. Gen Chem stuff. All right. Now what we're going to do is this electron will do a radical abstraction of one of the protons on benzene. And then another one of these radicals, or another one of these pi bonds, will dump in an electron. And this pi bond, or shoot, sorry, I'm goofing up here. I looked at my notes wrong. This is actually going to donate an electron directly to this carbon, not abstract a proton. I apologize. And then this one's going to dump its second electron down. This pi bond's going to dump an electron down. And then this one's going to dump an electron down. This is one of the few reactions I'll show you where drawing 5 arrows in one step is acceptable. All right, so let's try to account for the movement of all of our electrons. Sodium donated its electron, so now it's sodium plus, right? We still have this double bond on the left. That was untouched. What about this double bond right here? It got broken. Same with this double bond, so we don't have double bonds in those positions. Do we have any new double bonds? Yeah, on the far right. Okay, so we're halfway through the Birch reduction. If we're looking at electrons on the top carbon, you see how there's 2 single-headed barbed arrows pointing to that top carbon? That means we've got a lone pair up there, giving that carbon a formal negative charge. And then what about that bottom carbon? It's a radical. So in this case, we form a radical anion. And the next step in this reaction actually involves the methanol, where this negative charge will grab a proton off of methanol and get rid of that anion. So now we've got 2 protons. We still have these double bonds. Got protons off of all of the other carbons. And we still have this radical position. And then we form the conjugate base. All right, now we can do this again where sodium can donate another electron to this carbon. That way that electron's not all alone. And again, we form a new anion down on this lower carbon now, along with sodium that has a positive charge. What do you think the last step might be if we have more methanol floating around? Yeah, you're just going to add another proton from the methanol. Oops. Let me show this as a single bond. This will come grab a proton from methanol, clamp down. And we end up with our final product. This is a really important reaction, and it mimics biological systems. Oftentimes in your biology classes, you'll see movement of single electrons, not pairs of electrons. And this is done using biomolecules that actually have similar frameworks to this, where they can gain and lose electrons by switching between an aromatic molecule and gaining 2 electrons, similar to a Birch reduction. Yep.
Cyclic dying, could you like do H2 and catalyst to reduce that further?
Yeah, absolutely. So we could take this and reduce it further using relatively gentle reduction techniques. All right, now the tricky part with this is determining the regioselectivity. So let's take a look at this. So I'm going to throw up an example here. What's this compound called? Let me clean it up. Acetophenone, right? It's one of our parent names. It's one of the older IUPAC names that has stuck around. Let's say we do dissolving metal reduction. The question is, will our product have the double bonds here and here? Or will our double bonds be between here and here? We only use ortho, meta, and para when we're describing di-substituted benzene rings. In this case, it's not a benzene ring. But we do have different alternations of our double bonds, right? So the important thing to look at is the carbon. So if we look at this carbon gets reduced, right? If we think about this, we've got this substituent on here, and is this substituent electron withdrawing or electron donating? Withdrawing, right? If we draw resonance structures, you can actually draw resonance structures where you do something like this. You can take one of these pi bonds, let me erase this for a second, dump them up here and pull electrons up onto this oxygen. So if we think about it, it's not pushing electrons into the ring. If anything, it's pulling electron density out of the ring. So we can label this as an electron withdrawing group. And an electron withdrawing group is essentially going to make this carbon partial positive, right? And in this case, if this carbon is getting reduced, that means it wants to gain an electron, which makes sense if it's partial positive, right? Partial positive carbons want electrons. And in this case, which of the compounds was reduced? The left one or the right one for our products? The left one, right? If we look at this one gained a hydrogen, and it's also gained electrons in that process too. So if we look at this compound is not formed. This is going to be your product. It's a little bit strange that this one is not observed. However, it's all due to the electron withdrawing substituent coming off of the benzene ring. Let's take a look at a different example. What's this compound called? Anisole, right? Let's say we try to do a Birch reduction on anisole. Is anisole electron rich or electron poor? Is that methoxy group going to donate electrons in or pull electrons out? Let's try both ways. All right. We've got 2 lone pairs on the oxygen. Can I pull this pi bond out of the ring and form a new pi bond between carbon and oxygen? No, that would violate the octet rule on oxygen. However, what if we were to push this electron down and push this electron over? That's allowed, right? So in this case, the methoxy group isn't electron withdrawing. It's, in fact, electron donating. So let's take a look at this, and we'll circle this, and we'll say electron donating. And we'll take a look at this carbon right here. This carbon is going to be partial positive or negative? Negative. Partial negative, right? The ring is now more electron rich. If it's partial negative, does that mean it wants another electron? Does it want to be reduced? Yeah, probably not. It already has a high density of electrons on it. So if we look at this carbon does not want to be reduced. So which product do you think we're going to get? I want you guys to draw out your anticipated Birch reduction product. I'll draw both and then we'll circle the right one. Which one do you guys think it'll be, the left or the right?
The right.
The right. If we look at this one, we would say this one has reduced carbon, meaning that this one is not observed. Whoop. This one will be exclusive. So if we compare these two, you see how the double bonds in the top one were going vertically up and down? But with an electron donating group, they're now kind of going diagonally. You can more or less predict the outcome of Birch reductions by using this methodology. All right, I've got a challenge one for you guys. Let's say we've got acetophenone and a methyl group coming off. And we've got ammonia, we've got methanol, and we've got sodium, methanol, and ammonia. What product will we get out? Easiest thing to do, I would say, is circle your substituents, identify them as electron withdrawing, electron donating, predict whether or not that attached carbon wants to be reduced or does not want to be reduced. Is that electron withdrawing or donating? Withdrawing. What about a methyl group? This is a little bit tricky. It's bringing back that concept of hyperconjugation. That methyl group is sp3 hybridized. That sp3 lobe can actually donate a very, very small amount of electron density into the adjacent p orbitals. So methyl groups are actually slightly donating due to hyperconjugation. It's not due to resonance in this case. So if we look at this carbon, does this carbon want to be reduced? Yes. So I'll just say wants electrons. What about this carbon?
No.
Yeah, it does not want electrons. It's already got a donating group on there. All right, so let's try to predict our product. We'll draw both of them out again. So do we have double bonds here or here? Do you think it'll be the left or the right? Left, right? If we look at this, this will be observed because that top carbon gained electrons, it gained a hydrogen too. And the right one, the top carbon didn't gain electrons. Yep.
So what is that methyl group on carbon 4?
That's a good question. What do you do if you run into competing situations? Then what you have to do is essentially compare the strength of your electron withdrawing versus electron donating substituent. The stronger one will win out. And that's actually what we're going to talk about starting next term, is how to compare the strength of substituents. But we're going to kind of leave it for right now because I don't want to overwhelm you guys. So if I do give you a problem, they'll try to match. You won't be expected to know which one's stronger in terms of an electron withdrawing group. Was there another hand up? No?
So you wouldn't give us a problem where like the other substituent was like a ester or something, or not ester, ether.
I would try to have one where both matched and would only give you one product. You wouldn't have to try to figure out which substituent's more electron withdrawing or more electron donating. Yeah. All right. Do you guys want to see the mechanism for one of these, or do you want to go on to synthesis problems? Raise your hand for mechanism for Birch reduction. All right, there's a few people. Raise your hand for synthesis. A few people. How about this? We have 10 minutes. We'll do one mechanism for the Birch reduction, and then we'll do some synthesis. And I'm going to do electron withdrawing. These tend to be pretty common. And what I'm going to do is I want to do that acetophenone one again. But before we do this, I want you guys to help me draw all of the resonance structures for acetophenone. Yep. All the major resonance contributors. You don't have to do degenerate ones or ones that are super minor.
Oh, the double bond to the oxygen.
Yeah, let's give people a minute to work on this.
Oh.
How many of you guys think you got all the resonance structures? Getting close? All right, I'm going to draw out the skeletons at least. Save some time. All right, let's do some arrow pushing. First arrow, let's pull this electron up and this electron up, just like we saw in the example I did before. We'll fill in electrons. Means we've got a double bond here, 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 and we've got a negative charge on oxygen. Is that it? What am I missing? Positive charge, right? So don't forget about your charges. That makes a big difference. And then we can keep on pushing arrows. We can say, well, what if we move this pi bond up? Have double bond, double bond, double bond, oxygen negative, positive on the bottom, right? Then we can keep on pushing around the ring. We can say this one goes over here. And we've got double bond, double bond, double bond, negative charge, and positive. So let's consider our hybrid structure. Our benzene ring has all of these delocalized electrons. This is kind of a pseudo double bond. Whoops. This is also a pseudo double bond. And then we've got a partial negative here. We've got a partial positive here, partial positive here, and a partial positive over here. So let's use this hybrid structure when we consider our mechanism, right? We're going to start with the acetophenone. First step, we know that sodium will actually give an electron. The question is, which carbon will sodium give an electron to? Will sodium give an electron to this top carbon? Not quite. It's going to aim for one of these delta positives, right? Specifically, the one on the opposite side will be super accessible because there's no sterics there. So sodium will take this electron. It will donate it in. One of these electrons will get donated over. One of these electrons will get donated over here. One of these electrons will get donated over here. And one will get donated at the top. So the key is remembering that sodium's going to donate an electron to one of that delta positive portions of the molecule, not any of the other carbons. And it usually goes after that para position. All right, so now we've got two electrons down here. We've got our radical anion. The next step that we have is deprotonation of methanol. This lone pair will grab that proton, kick this over. Now we just have our radical position to worry about. What will happen with that radical? It needs another electron, right? It's assumed that we have excess sodium around, so this sodium will donate its electron.
There's no excess sodium, you just stop there.
Yeah, but radicals are inherently really unstable, so it desperately wants to pair that electron as much as possible. And then the next step, again, we've got methanol. And this will come grab a proton, clamp down. And voila, you've got your final product. I'll put the complete mechanism for an electron donating example in the notebook, but I know some people wanted to go on and practice some synthesis problems. It's pretty similar. You just want electrons to go to carbons that are either partial positive or neutral. Electrons don't want to go to partial negative centers, right? So if you've got an electron donating group, you want to avoid donating electrons from sodium to those partial negative centers. Any other questions? Sorry, I thought we'd have more time today. We'll do a quick synthesis practice. So we'll try to make acetophenone from isopropyl benzene. Tricky. Before we begin, the first thing I always recommend doing is count carbons. Did you gain or lose carbons? Typically, if we're gaining carbons, that means we did some sort of ring opening of an epoxide, a Grignard reaction, something like that. Looks like, in this case, we lost a carbon. How can we lose carbons? Ozonolysis, right? So use clues like that and then try to work backwards and ask yourself, well, how can I make a ketone? We know ozonolysis might be involved. What would the intermediates be in order to get from point A to point B? You guys can talk to one another too. It's not an exam. I won't yell at you. All right. I think a lot of people are over-analyzing this, right? Ozonolysis. We can make a ketone directly from ozonolysis, right? So let's work backwards. We know that O3 and DMS will give you a ketone. What does that mean our intermediate was? An alkene.
Double bond.
So we had some sort of double bond right there, right? And then ozone will come through, clip that double bond. We'll make CO2 in our ketone. Now the question is, well, how can we get from there to there?
Elimination by NBS.
Elimination, right? We just covered this where we said NBS
You got bromine
and UV light will do radical bromination. And then a strong base can give you your double bond. So tomorrow, if we have time after the exam, I'll throw up some more practice problems. But this is kind of tying in the new benzylic chemistry with previous chemistry. All right, I'll see some of you guys in lab.